I'm Felipe, and I will be presenting about the paper Comparison of Sampling-Based Path Planners for Robocup Small Size League. The authors of the paper are Felipe, Marcos, and Takashi. And first of all, I will be explaining about the outline of this work, and we will start with the introducing the problem and our motivation. After that, we will explain the background knowledge for this, and the simulation that we did in order to achieve the results that we are about to discuss. Finally, we will get to the conclusions and the acknowledgements citing our most important partners for this work. Introduction. We are part of a robotics team, 8 androids, and we compete in the Robocup Small Size Soccer League. You can see a robot picture in the right and the omnidirectional four-wheeled robot, which has its top view shown in figure B. So in this competition, we have a path planning problem with short planning time requirements, and because of that, our motivation as the league, we would like to compare recent sampling-based approaches for path planning problems and to check which one of the approaches has the best performance comparatively to the other reported approaches. So as a basic literature review, initially in 1998, RRT was proposed as a initial path planning solution, and the extended execution RRT was an improvement of RRT in 2006. It's a very widely used algorithm throughout the league. Also, as of 2010, there was a big enhancement over all the path planning algorithms. So we can cite RRT star in 2011 by Frazzoli, Jason and Pavone in 2013 with fast marching trees, and batch informant trees in 2014 with Gamel. In 2019, we have a comparison of A star and dynamic visibility graph in the context of the league by Tony Dandel. And finally, we have many reports telling us about the use of path planning solutions across different teams in our league. Following now the background, we have to present the path planning problem. So there are two basic approaches. As we talk about path planning, we can approach the problem as a graph-based path planning or a sampling-based path planning. We would divide the state space into two parts, the obstacle space and the free space. And our main goal is to find a path connecting an initial state to a goal state. And the optimal path planning problem is, of course, to attempt to find the best path in terms of length. It's a optimization problem, and the path must also be a feasible path. Therefore, it must not cross any obstacle. The first algorithm that we are going to talk about is the RRT. RRT has a characteristic of the goal bias, which is basically the probability of your tree to grow towards the goal. You can check the main two steps of RRT in figure A and B, and there is a improvement of RRT in ERRT, in which there is a waypoint bias. Therefore, the author suggested us to use a bias towards previous solutions. And finally, in 2011, the RRT star was a suggestion to create a asymptotically optimal approach, in which you can see in figure A, B, C, D, and E. He adds up the step of rewiring to RRT, which is fundamentally the basis of the optimality. The fast marching trees algorithm is basically it uses a data structure, a RDIS graph. You can check in figure 3. Basically, it samples n states from the free space, and it does lazy collision checks. It performs lazy collision checks in a way that it firstly attempts to find the best path across the graph using graph-based approaches, and then after finding the best, it attempts to check if if that path crosses any obstacle. Finally, the batch informant trees is another approach. Also uses the idea of graphs and graph search based approach, but it uses samples from state space, and it iteratively creates denser graphs that they call it a batch. Every batch is another graph that finds a path, and using that path it performs a construction of a boundary, elliptical boundary. This boundary is reduced iteration to iteration, reduced in terms of area, and it relies on the idea of informed search that you can check in the paper of Gamble. Now, the simulation experiment. For the simulation, we used the setup of this computer, and we also used the OMPL library. We tested the full implementations of all of these algorithms, and we created a modification of the OMPL base code, RRT base code, to test the ERRT performance in C++ language. And all the obstacles that we are about to simulate are static. Moreover, we created a Monte Carlo simulation with 10,000 iterations per metric that we are about to emulate. So this is the field, how we dispose of the field. So we created like 3 regions. One region as the initial region, other region is the obstacle region, and then finally the goal region. We randomly pick one initial state and one goal state in each corresponding region, and we attempt to create a path connecting both states. So as a result, finally we attempted to tune the number of samples of BIT star and FMT star, which was about 200 samples, and as the goal bias we elected 70% as a good number. You can check the plots of each one of the parameters and the performance in terms of success probability, varying each corresponding parameter. So in each situation we approached a number close to 100%. So per metric, the first metric is the success probability in terms of the maximum allowed planning time. The shorter the planning time is, the harder it is to get a succeeded solution. The second metric in figure C is the average path length. So the more time we allow the planner to perform, the shorter the plan, the shorter the path found is, due to convergence optimality. This is more clear for BIT star than for the other planners. In case of RRT star, the convergence performance is very poor. This is also very reported in the literature. The third metric would be the standard deviation, which tells us how much the path varies when the planning time increases. The best performance was of BIT star and FMT star secondly. And the final metric was the average distance to the goal. We created a ideal tracker, and we compared like all the planners. The best performance was BIT star, which reached the goal faster, and FMT star also had a good performance, ERRT2, comparatively to the others. And now our major conclusions. So we can see potential of using these 2 algorithms in the league. RRT star had a poor convergence rate, RRT had a poor path variance, and we can check good comparative performances of BIT star, FMT star, and ERRT for in terms of tracking performance. Finally, the authors would like to thank our sponsors, and I would like to thank FAPESP for the master's scholarship according to this number. These are our sources, and I will be available in case of any questions.